going to do another example, 1 or 2 or 3. Like I said last video, this is a particular topic. I would put this as number 2 in terms of importance. Number 1 would be solving 2 equations and 2 unknowns by substitution. And completing the square I would put as a close second. I mean, this is just a skill you absolutely want to have under control. You shouldn't have to refer to your notes. You really want to know this. And there's plenty, thousands, tens of thousands of examples on YouTube. Let me do another example. Let's go ahead and do it. We'll see what happens here. Let's say we had 5x squared minus, I don't know, 15x plus 50 equals 0. Now, to complete the square, I'm going to go over those 6 steps that I did in the last video. First step is get the plane number over on the right-hand side. There are more technical ways to express this, but yeah, I think you get the idea. And if not, I can certainly, some videos will express it, or textbooks will express it. You could say subtract the coefficient of the 0th term from both sides. And you see what I did. Divide both sides by the coefficient of x squared. So far so good, no problems. We'll take the coefficient of x divided by 2, square it, and add that to both sides. So in this particular case, that would give us 9/4. Remember, I went over in the last video how you get the 9/4. I just said it right now, but I didn't write it down, which is pretty typical. It's kind of the tradition. That's so easy to do. Nobody really wants to see it done. Let's factor the left side here, x squared minus x squared. X minus 3/2 squared, and then we'll add this up here, negative 31/4. And then we'll square root both sides, and then we've got to stop because we need to talk about what on earth does it mean to take the square root of a negative number. Now, if you've seen this before, you've done this before, fine, but I really, right now, would like to think or pretend that you've never taken the square root of a negative number, never seen it done, you've never contemplated it. This is a new thing and we want to discuss. So I'm going to, because right now, I mean, what does that even mean? Maybe it doesn't mean anything. So let's put that on hold for a second. And let's take a look at something pretty easy. Well, maybe not. I don't know. Square root of negative 9. What is the square root of negative 9? Could it be 3? No, because 3 times 3 is 9. So it's not 3. And could it be negative 3? Well, negative 3 times negative 3 is 9. So it's not negative 3. So whatever this is, if it is anything, it is not 3 and it is not negative 3. So, maybe I don't know if I should do this, but it is not 3. And it is not negative 3. So whatever you think it is, not that, or it's neither one of those. But the question still stands. And one possible answer is there's no such thing. Whoever said there had to be such a thing. And this was the position in mathematics up until around the 1500 AD. And that's when people started wanting to be able to do this. Now, we could go back a little bit further in time, and I could ask you for the solution for this. And if you were an ancient Babylonian or an ancient Egyptian or even an ancient Greek, you would have looked at this and you would have said, there's no solution. What could you add to 1 to get 0? There wasn't a solution until somebody, and I actually don't know who, but somebody came along and said, well, I would like this equation to have a solution. I would just like it to have a solution. So I'm going to create a new kind of number, and in fact, that number is negative 1. And as a matter of fact, the definition of negative 1 is it is the solution for this equation. That is the actual definition of negative 1. And if you think about it for a minute, negative numbers are actually highly abstract. I've shown you a drawing of the square root of 2. And down the road, I'll show you a drawing of pi. Those are easy to show. I can show 2/3, and I can show the number 8. I can even show 0. Look at the room you're in. My suspicion is right now, if I ask you how many elephants do you see in the room, the answer is 0. But try to show me -1 of anything, and you might be tempted to say, well, here's a number line, and there's 0, and there's -1 over there, and there's 1. But why is this -1? Is because it's a distance, because it is at a distance of 1 from 0. We just by convention say if we go to the left, we call it negative, and the right, we call it positive. But the distance itself is still 1. It's not a negative number. So what am I getting at here? What I'm getting at here is that -1 is a very abstract concept, but you've gotten used to it, and you probably don't have any problems with it. You feel content and happy to do mathematics with negative numbers. And we're going to do a similar thing here. We're going to create new numbers. I mean, they've already been created. They were created in the 1500s, as far as I know. And we're going to call this 3i. Now, the I stands for imaginary, because at first people would have said, well, you can't even show me this 3i. It's like an imaginary friend. I mean, you can't even show me this. So it doesn't sound very real to me. Now, these numbers they're not real numbers, but they have philosophically equivalent status of being real as does any other number. But this I has stuck. And I don't have a problem with it, and it's stuck, and we're stuck with it. Now, what is 3i? By definition, 3i is the square root of -9. I mean, that is actually what it is. And the square root of, let's say, -1 is 1i, or just I, and the square root of -25 is 5i. Again, we declare this. You can't figure this out. We declare this to be true. So if you're struggling to figure out why the square root of -25 is 5i, there's nothing to struggle with. What's a face card worth in blackjack? 10. Why? Because we declare it. What's a goal in soccer worth? 1 point. Why? Because we declare it. So what is square root of -25? 5i, because we declare it. Now, on top of that, we're also going to say, well, there's a plus and minus to each one of these. And no one normally writes this down, but what is -3i? Well, it really is -1 times 3i. Now notice if we square this by our rules of exponents, if we square this, we can square the first term and multiply it by the square of the second term. But 1 squared is 1, and 3i squared is 9. So you do in fact get 9. So yes, we can take the square root of a negative number, and I'm not sure how much else we want to say, or I want to say about this right now. Are these imaginary numbers useful? And the answer is absolutely. If you go far enough, particularly in chemistry or physics, electrical engineering, mathematics, yes, tremendous uses. That's pretty surprising. We wouldn't be able to understand the structure of the atom without them. And that should seem like a rather hard to believe thing. That what I just said should seem rather hard to believe, or maybe leave you feeling incredulous, but yes, they are important. Are we going to see in this course why they're important? No. You'll have to take many more courses to find out why they're important. So right now, you could just think this is some bizarre thing that you're being tormented with. Okay, now, back to that equation where we had a negative root. Well, I forgot what that equation is, so let me write down a different one, saying -3x squared. How about minus, I don't know, 12x plus 15 equals 0. Well, let me make this a slightly different number here. How about plus 18? Okay, let's complete the square. Get that number over on that side. Divide both sides by the coefficient of x squared. We're going to take the coefficient of x divided by 2, square it, add to both sides, happens to be 4, fine. Factor this side, factors in that no-brainer way that I discussed in the last video. Okay, -2, square root both sides. What's the square root of -2? Plus or minus the square root of 2i. And again, it may just seem like this little game we're playing with, the square root of a negative number, and we just take the square root of the positive number, but put an I after it. Yeah, and that's what we're doing. Yeah. So I have to say, the fact that this is useful is a very remarkable and unexpected thing, and yet it is true. Subtract 2 from both sides, -2 plus or minus the square root of 2i. And there are the solutions for this equation. There are two solutions. One is -2 plus the square root of 2i, and one is -2 minus the square root of 2i. So there are two solutions. So you complete the square, and your answer may wind up being a rational number, an irrational number, or a number like this. Now, when you combine a real number with an imaginary number, we call it a complex number. I suppose for the obvious reason that they're complex. And for right now, I'm not making any attempt to show you what is the meaning of these imaginary and complex numbers. So it may leave you feeling uneasy. In fact, you know what? It really should. Because again, if someone says, "Can you show me 2/3?" It's not a problem. There, the shaded region is 2/3. You see it. It's a drawing. It's physical. It's real. If someone said, show me the square root of 3, I would take that triangle, the famous triangle we talked about, and there's the square root of 2, and I draw another triangle like this. There's another right angle, and that's the square root of 3. That length is the square root of 2. And if you draw a circle and make the diameter 1, cut the circle, stretch it out like that, that length is pi. That length is pi. Notice pi is not going forever. It's more than 3 and less than 4. Approximately 3.14. We can talk about how would you even know such a thing. We'll do it another time. But what's my point? You want to see pi? You're looking at it. You want to see square root of 3? You're looking at it. You want to see 2/3? You're looking at it. If you want to see 3i, I don't have a particularly satisfying way of showing you 3i. I have a way of showing you, and it actually, well, maybe I should show you. Look, it's analogous to negative numbers. See, if you went back and you talked to an ancient Babylonian and you said, I'm thinking of the number -5, and they would say, what are you talking about? What is -5? I've never seen -5 apples or -5 oranges or -5 feet or something that weighed -5 pounds. Like, I don't know what you're talking about. And what you would do is you would draw a number line, no doubt, and you might say there's 1, 2, 3, 4, 5. And then over on this side, you would say -1, -2, -3, -4, and -5. Now, whether or not they felt happy with this answer, I don't know. You'd have to ask them. But we'd say, well, if we start from 0 and we go to the right, we'll call those numbers positive. And if we go to the left, we'll call those negative. This is, one way of doing it. When it comes to these complex and imaginary numbers, we extend this idea. And we can do the following. We can say this is the x-axis, but now we want to think of this as the real number axis. And there's several ways to write this, but let's just say this is sort of the real, R-E-A-L, real number axis. And we'll think of the y-axis as being the imaginary, say capital I, the imaginary axis. And if you take any point here, remember it has an x and a y coordinate? Well, now it has a real coordinate and an imaginary coordinate. And let's suppose I go over 1, 2, 1, 2, 3, 4, 5. This point right here is the point, here, I'll write it like this. We're going to write it like this, 2 plus 5i. And this arrow, or if you want to sound fancy, you can call it vector. But this arrow, this vector, is the number. It is the complex number. Now, right now, I don't want you to worry about this, but what the heck? Maybe I thought, there, you should see this. So the complex number 2 plus 5i is that arrow. I guess you're looking at it. That answer didn't make me feel particularly content the first time I saw this, or the second time, or the 100th time I saw this. At some point, you just start to, just like negative numbers, you just sort of, I don't know, start to feel okay about it, and can work with them and see their utility, and so on and so forth. Okay, now, I need to flash back to, let me get the right section here. Where was this? Yes, 8.8, so complex number system. The complex numbers. So there, I'll write this on 8.8. I said we'd be coming back to that. And I knew this would motivate us going back there. Because at first, we didn't have a reason to deal with complex numbers. But it turns out that, and we're going to see some limited uses in this course when we graph parabolas. But the complex numbers, this is a symbol people usually use. We're not going to use that. I think somewhere way back in the distant past, I showed you the symbols for the natural numbers and the integers and the rational numbers and the real numbers. And there's a symbol for the complex numbers too. But any number that looks like this, say 3 plus 2i. So you have a real number and you add or subtract, but you add an imaginary number. This is called a complex number. And we can add them, subtract them, divide them, and multiply them. And this is, what did I just say, 8.8. Now, adding them, you do exactly what you think that you would do. So, for example, there's right there, I'll put parentheses to emphasize, that is a complex number. And let's add another complex number to it. Let's say we had 7 plus negative 8i. Well, you can treat this like adding like terms. We add the real terms, 3 plus 7 is 10, and then you add the imaginary terms, 2i minus 8i is negative 6i. And you do the same thing for subtracting. And there's practice problems in the book, but the good news is adding and subtracting, you do it just the way you would think. So not a whole lot to be said about that, except what does it even mean, when I'm adding two complex numbers? Let me think about whether we want to talk about that or not. So for right now, I can just say, hey, there's a game we're playing, and the game uses these things called complex numbers, and this is how you manipulate these symbols. There is a meaning for this, and it's visual, but I'll just leave it at that for now. But what about multiplying? So suppose we have 4i minus 3, and we want to multiply this by 2i plus 5. Here's the good news. Basically do this the way you think, because look at that. It looks like it's set up to do the FOIL method. And lo and behold, that's exactly what we do. So we'll take 4i times 2i. Now think about this for a second. 4i times 2i. That's 8i squared. But by definition, I squared, I times itself, is negative 1. We declare that. That is the very definition of I. I is equal to the square root of negative 1 by definition, so I squared is negative 1. So what that gives us here is negative 8. That's this times this. Then this times this is plus 20i. This times this is minus 6i. And this times this is, ordinary arithmetic, negative 15. 20i minus 6i, 14i, and negative 8 minus 15 is negative 23. So the good thing about multiplication is, just like addition and subtraction, if you just did what came most naturally, you would be doing the right thing. That's pretty good. But what about division? Well, division it's not as obvious. It's not as obvious what to do about division. So suppose we had 3i plus 2 divided by 5i minus, let's just say 4. How does one do this? Or, how do you go about doing this? Well, let me just show you. I'll just show you. What we're going to do is multiply top and bottom by the conjugate of the denominator. What does that mean? Well, I used that term conjugate a while back when we were talking about polynomials, and I haven't used it since. But it does come up on a regular basis, and it's worth knowing. If you have two things added together, a plus b, its conjugate is a minus b. And you could take the mirror image of this. If you have a minus b, its conjugate is a plus b. So something has to be a conjugate relative to something else. Something has to be in relation to something else to be a conjugate. You can't have a conjugate all by itself. This is a conjugate of that. So what is the conjugate of, remember we did conjugates in terms of special product. A plus b times a minus b is a squared minus b squared. So what is the conjugate of the denominator? It is 5i plus 4. So we're going to multiply top and bottom by 5i plus 4. Now up top, what are we going to get? 3i times 5i. Remember the I squareds give you -1. So that's -15. 3i times 4 plus 12i, 2 times 5i, plus 10i, 2 times 4, plus 8. In the bottom here, we actually have a special product. We have a minus b times a plus b. It's the FOIL method, but it's one of our special products. So we get the first thing squared, which is -25. Because 5 times 5 is 25, and I times I squared, which is -1. And then minus, oh, I have a typo here. Look at that. Plus 4. Plus 4. So minus 16. Now what happens here? Let's go ahead and add like terms up top. We have 12i, 10i, so that's 22i. And then -15 plus 8, which is -7 or -7. And down here, what do we have? We have -41. And now I'm going to unadd these as fractions. Again, I mean, you'd be amazed. It's not going to stop. The whole idea of learning fractions, like I said, it just keeps coming back to haunt people. And hopefully you've all mastered your fractions now, but if not, it's still going to come back to haunt you. So this is -22 over 41i, and then plus 7 over 41. And normally we would write this like this: 7 over 41 minus 22 over 41i. So equals. And that is it has the form of a complex number. It's a real number plus or minus an imaginary number. And so how do you divide one complex by another complex number? You multiply top and bottom by the conjugate of the denominator. Is this difficult to do? No. What's difficult, a little more difficult, is to say, what does this even mean? You know, it's relatively easy to explain. If you have 12 divided by 4 and say 3, that's a relatively easy thing to explain. What does that mean? Well, you could say 4 goes into 12 3 times, 4 8 12, 4 8 12. Or you could say 4 times 3 is 12. That's sort of not too difficult to explain. It is more difficult to explain what this division means. So I probably won't even address that in this course. I probably will address addition, subtraction, probably multiplication. Division we'll just put on hold. So for right now, just make sure that you know how to add, subtract, divide, and multiply complex numbers. And if you feel uneasy, that's absolutely to be expected. I think it is. It would be, but on the other hand, you may go, look, these are procedures, follow the procedures, and get the answer. Okay, so that'll finish this video. Next video, we're going to take quadratic equations, and well, we're going to be solving equations that don't look like quadratic equations, but they are. They're just in disguise. So I usually refer to them as quadratic equations in disguise. Books refer to them as different things. Hey, let me write one down. You try this. I'm going to write an equation down. Try solving it. Don't look at the book. Don't look at videos. Just sit down and take a bit of time and see if you can get this. You have all the skills. We haven't done it in this course yet. So think of this as a challenge, and then next video, I'll solve it. So say we have the square root of 3x minus 1 plus 2. So that 2 is not underneath the square root sign, equals the square root of, let's say, 2x plus 3. So think of this as a challenge. Try solving this problem, and I'll solve it on the next video.